shining stars, the burning sun. Thanks to the light and heat pouring down from our sun, civilization arose on Earth, with humans then going on to create even more sophisticated cultures. However, global warming, environmental destruction, resource depletion. With today's society consuming such vast amounts of energy, the Earth is now raising a cry. Our energy resources are limited. It is said that our supplies of oil and other fossil fuels will be completely exhausted in 50 to 100 years. Humanity now faces a crisis. To sustain our advanced civilization and pass along the abundance of our societies to the children of future generations, we must achieve nuclear fusion power generation, a new energy resource that has little environmental impact and can be derived from seawater. For the sake of our children's future, research is being conducted in Toki City, Gifu Prefecture, Japan, for the development of nuclear fusion power generation as a future source of energy. The National Institute for Fusion Science, or NIFS, is conducting basic research with the Large Helical Device, or the LHD, with the aim of achieving nuclear fusion power generation. What is this energy source of the future known as nuclear fusion? Nuclear fusion refers to a reaction in which lighter nuclei collide with each other and fuse, resulting in a heavier nucleus. In fact, this nuclear fusion is what makes the sun shine. Hydrogen in the sun undergoes fusion, and the energy thus created is what causes the sun to shine. The number of neutrons that comprise the nucleus varies, and in the case of hydrogen, this results in isotopes called deuterium and tritium. Isotopes of hydrogen are used on Earth to create nuclear reactions that produce energy. Nuclear reactions between light elements, such as hydrogen, result in less mass after the reaction. The missing amount of mass is converted into an enormous amount of kinetic energy. This is expressed by Einstein's equation E equals mc squared. This equation expresses the fact that mass is equivalent to energy. The speed of light, c, is so great that light circles the Earth 7.5 times in 1 second. Thus, we can see from this equation that even a small mass can be converted into an enormous amount of kinetic energy. For example, the energy derived from just 1 gram of nuclear fusion fuel is equivalent to that in 8 tons of oil. Since fusion fuel can be produced from seawater, it is essentially inexhaustible. The realization of nuclear fusion can provide humanity with an endless supply of energy from the ocean. For nuclear fusion to occur, atomic nuclei must collide into each other at high speeds. How can this be accomplished? One method is to use high temperatures. The higher the temperature becomes, the more active the motion of the matter becomes. At several thousand degrees Celsius, the nuclei and the electrons scatter and fly about. This state is known as plasma. But the nuclei in a plasma state have a positive electric charge. Thus, they mutually repulse other nuclei. Further increasing the plasma's temperature, however, eventually allows the nuclei to overcome the repulsive force and collide, thus creating nuclear fusion. To achieve nuclear fusion here on Earth, we must confine the plasma in a stable, high-temperature state of 100 million degrees Celsius or higher. NIFS is moving forward with 3 research projects aimed at realizing fusion energy here on Earth. The LHD leads the world in nuclear fusion research. The LHD includes various different types of equipment in a complex form. This is the main part of the LHD, the unit that confines the plasma. Inside the LHD, we can see the device's complex configuration. High-temperature plasma is confined in a torus or a donut shape within this apparatus. But how does one confine a high-temperature plasma reaching 100 million degrees? Atomic nuclei in a plasma state carry a positive electric charge, while electrons carry a negative charge. Such charged particles move around the magnetic field lines. According to Fleming's left-hand rule, the motion of an electrically charged particle generates an electric current. In a magnetic field, the electrically charged particle is subject to forces in a perpendicular direction and is thus bound by the magnetic field lines. Here, nuclei and electrons flow in a spiral motion around the magnetic field lines. In fact, this is exactly what occurs in an aurora, when the plasma emitted by the sun is trapped by the Earth's magnetic fields. This means we can confine the plasma by using electromagnets to create a donut-shaped cage of magnetic field lines. However, because the magnetic field lines are curved into a donut shape, a centrifugal force acts on the nuclei and the electrons that are moving along these lines. As the nuclei and electrons rotate in opposite directions, the action of the centrifugal force produces an uneven distribution, with the nuclei more toward the top and the electrons more toward the bottom. This action of the nuclei and the electrons prevents stable confinement. The solution to this problem requires the creation of a cage of twisted magnetic field lines. There are 2 principal ways to accomplish this. The first way is to use a tokamak configuration to produce a helix by running a current through the plasma. However, with a cage of twisted magnetic field lines using only coils, we now have a helical system developed independently using original Japanese concepts. The word helical means twisted or spiral. The LHD is a helical system. The LHD produces a cage of twisted magnetic field lines using only helical coils. This twisting component is the helical coil that generates the magnetic field lines. Twisting the magnetic field lines prevents uneven distribution of the nuclei and the electrons, enabling stable confinement of the plasma. The LHD is comprised of a variety of different devices. The main LHD unit confines the generated plasma. Vacuum pumps create an ultra-high vacuum inside the vessel, which generates the plasma. These pumps are capable of creating a vacuum nearly equivalent to that in space surrounding the International Space Station. This system supplies liquid helium to the superconducting coils that generate the magnetic fields which confine the plasma. The coils are cooled very slowly over approximately 1 month to minus 270 degrees. These devices heat the plasma. The plasma is heated through the injection of high-energy particle beams. These are also heating apparatuses. Functioning like a microwave oven, these units heat the plasma with radio waves. The LHD also includes measuring equipment and many other types of devices. From this room, we control remotely the experiments in confining plasma conducted with the LHD. Plasma performance has improved steadily year by year. In addition, we have succeeded in sustaining high-temperature plasma for 1 hour, thus demonstrating steady-state operation, which is a distinctive feature of the helical system. Going forward, the achievement of nuclear fusion will require research in higher temperature, higher density plasma. This requires experiments using deuterium. The use of deuterium improves plasma performance and enables more precise study of the plasma approaching nuclear fusion power generation. In experiments using deuterium, a small portion of the deuterium gas undergoes a nuclear reaction, but as the tritium and radiation generated is recovered and shielded, they have no effect on the environment. Safety management at NIFS is comprehensive and thorough, including on-site environmental radiation readings and other measures. With ion temperatures reaching 120 million degrees in deuterium experiments, we foresee the realization of fusion power generation. Simulation research to predict the behavior of plasma confined in nuclear fusion devices is essential in ongoing experiments. NIFS's Numerical Simulation Reactor Research Project makes full use of our supercomputer, Plasma Simulator, as we conduct research to discover the physical laws that govern phenomena occurring within the plasma. A particular advantage of the LHD is that, in principle, it can operate for longer periods of time. In order to construct a power generation station that exploits the advantages of this helical system, the Fusion Engineering Research Project is examining designs to determine what fusion power generation stations of the future may look like. Issues of critical importance to that aim include research into powerful superconducting magnets used to create the cages of magnetic field lines to confine the plasma. Designs for systems to extract energy from nuclear reactions and generate electricity from that energy. Development of durable new materials and other topics. The Fusion Engineering Research Project is advancing state-of-the-art engineering and research together with collaborators in Japan and abroad. As an inter-university research institute, NIFS engages in academic exchanges with leading universities and research institutions, both in Japan and abroad, and actively promotes collaborative research with over 200 universities and research institutions. We are bringing together the world's wisdom to promote research and development and are building the scientific foundation needed to achieve fusion power generation. Fostering young researchers is another important role for the Institute. NIFS also oversees graduate school level education for the Department of Fusion Science in the School of Physical Sciences at the Graduate University for Advanced Studies, which is also known as Sokendai. The Institute also accepts graduate students from many universities as special joint researchers. As an affiliated graduate school, we also conduct graduate school level education in cooperation with various universities, including enrolling graduate students from a number of universities in Japan. Working for our children's future. Through ongoing research, the National Institute for Fusion Science continues in the quest to develop fusion power generation as a new and stable energy source.